Okay, if you watched the last video, we talked about or introduced the concept of the slope field where we're given a derivative and we've got this little grid of slopes, the value of the derivative at any given point. But the question is, where did that little grid of slopes come from? Let's look at an example where we don't have a function. Instead, we have a derivative that we don't really know a whole lot about, which is dy dx equals x plus y. And I'll give you an initial condition in a minute or so. But let's start by just talking about x plus y is our derivative. Well, 1, 2, 3, 1, 2, 3. 3, 1, 2, 3. Let's think about what happens when x equals 0. The derivative, the slope of my function, is just the value of y. So if x equals 0, I have let's do this in color, slope of 0, a slope of 1, a slope of 2, a slope of 3, a slope of -1, a slope of -2, a slope of -3. All right, so let's move on. What happens when y is equal to 0? Well, the derivative of my function is equal to the value of x. So, once again, we will say that here the slope must be 1, the slope must be 2, the slope must be 3, the slope is -1, the slope is -2, the slope is -3. So what else? Well, we could, plug in every possible value, but let's look at this one. Let's talk about, well, what happens when the slope is equal to 0. In other words, x plus y is equal to 0, then x is equal to -y. The slope will be equal to 0 when x equals -y, or more easily thought of, y is equal to -x. The slope is equal to 0 here, 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 just everywhere along the line y equals -x. So what else could we do? Let's do one more and see if we can sort of fill this in. What about when, in general, the slope of this function is equal to 1, x plus y is equal to 1, y is equal to -x plus 1. And again, what I see is I see that I have on the line -x plus 1, I have a slope equal to 1. So let's generally think about what happens here. As y increases, slope increases. Again, holding x steady. If y increases, the slope increases. Holding y steady. As x increases, the slope increases. And I've actually got a copy of the slope field here. What would it look like if we filled it all in? Let me bring this over and paste it in. Oops, shoot. Sorry, gotta use keyboard shortcuts on this one. And here's what this looks like if we fill it all out and use a slope field program. Remember, the derivative of y with respect to x, the slope of my function is equal to x plus y. So let's add an initial value to this problem. Let's say that I am told that this function, my original function, goes through the point 2, 0, Well, 2 comma 0 is right there. And if I follow the slopes, I see that it goes up very steeply from here, and that it flattens out very quickly right about there, and then goes back up steeply, which means that this function has an asymptote on that line right there. But there's a graph of my function. This is a graph of y equals some function of x. And notice I started with a derivative that was a function of x and y. I now have the graph of the function y equals f of x. Now, do I know the equation? Haven't the foggiest. But it doesn't matter, because based on this, I can now work with this function. If you told me, well, when some x is equal to, I could go to this graph and say, well, it looks to me like our function is going to be about using the slope field. All right, so my students, why don't you go ahead and do exercise 35. Again, I'm going to chop this off right here. I'm going to call this a quick example video, and we'll be back with one more example of slope fields in the next video. All right, thanks for watching and have a great day.